Metadata, assemblies, and the manifest are three core building blocks of the .NET architecture. They work together to describe, organize, and execute managed applications. While developers mostly interact with source code and libraries, the Common Language Runtime, CLR, relies heavily on metadata and assemblies to understand how an application is structured and how it should run. Without these components, features such as language interoperability, reflection, versioning, and security would not be possible in .NET. In traditional programming models, type information and implementation were often stored separately. Header files described types, while compiled binaries contained implementation. This separation caused synchronization problems and version conflicts. .NET solved this problem by embedding complete type information directly into compiled files. This embedded information is known as metadata. Metadata is structured information that describes the contents of an assembly. It includes details about types, methods, fields, properties, events, parameters, return types, access modifiers, inheritance relationships, and referenced assemblies. Metadata acts as a self-describing mechanism that allows the CLR to fully understand the structure of a program without requiring external files. Every .NET assembly contains metadata. When the compiler generates IL code, it also produces metadata tables that precisely define each type and member. This metadata is standardized and language neutral. Because of this, the CLR can work with assemblies regardless of the language in which they were created. Metadata is essential for enforcing the Common Type System, CTS. The runtime uses metadata to ensure type safety, validate method calls, and verify that operations are legal. When one assembly references another, the CLR reads metadata to confirm that reference types exist and are compatible. One of the most powerful features enabled by metadata is reflection. Reflection allows programs to inspect their own structure at runtime. Applications can discover types, read attributes, create instances dynamically, and invoke methods without knowing their definitions at compile time. This capability is heavily used in frameworks, dependency injection containers, serialization libraries, and testing tools. Metadata also eliminates the need for separate header files. Since all type information is embedded in the assembly itself, there is no risk of mismatch between declarations and implementations. This greatly improves reliability and maintainability. Attributes are another important feature built on metadata. Attributes allow developers to attach additional information to types and members. These attributes are stored in metadata and interpreted by the runtime or frameworks. For example, attributes are used for validation, routing, security, and configuration in modern .NET applications. Assemblies are the fundamental building blocks of deployment and execution in .NET. An assembly is a compiled unit that contains IL code, metadata, and a manifest. Assemblies provide the logical grouping of code and serve as the smallest unit of versioning, security, and deployment. An assembly can be either an executable file or a dynamic link library. Regardless of its form, the internal structure remains the same. Assemblies define boundaries for type visibility, dependency resolution, and runtime loading. Assemblies can be private or shared. Private assemblies are used by a single application and are typically stored in the application directory. Shared assemblies can be used by multiple applications and may be stored in a shared location. This model helps manage dependencies efficiently. One of the most important advantages of assemblies is strong version control. Each assembly has a version number that includes major, minor, build, and revision components. The CLR uses this version information to load the correct assembly at runtime. This mechanism prevents the classic DLL hell problem that plagued older Windows applications. Assemblies also define security boundaries. Permissions can be applied at the assembly level, allowing the runtime to enforce execution rules. Although modern .NET relies more on operating system security, assembly-level boundaries remain important for isolation. Assemblies support side-by-side execution. Multiple versions of the same assembly can coexist on the same system without conflict. Each application can bind to the version it was built against. This is possible because assembly identity includes version, culture, and public key information. The manifest is a critical part of an assembly. It acts as the identity card of the assembly. The manifest contains information such as the assembly name, version, culture, strong name details, and the list of referenced assemblies. It also defines which files belong to the assembly. When the CLR loads an assembly, it first reads the manifest. The manifest tells the runtime where to find dependent assemblies and which versions are required. Without the manifest, the runtime would not know how to resolve dependencies. The manifest also plays a major role in assembly binding. Assembly binding is the process by which the CLR locates and loads referenced assemblies. The runtime uses information in the manifest to locate assemblies in the application directory, shared locations, or configured paths. Strong named assemblies include a digital signature stored in the manifest. This signature ensures assembly authenticity and integrity. If a strong named assembly is modified, the signature becomes invalid and the CLR refuses to load it. This mechanism improves security and trust. The manifest also supports culture-specific resources. Assemblies can include satellite assemblies for localization. The manifest helps the runtime load the appropriate resource assembly based on culture settings. From an execution perspective, assemblies are loaded into memory by the CLR loader. The loader reads metadata and manifest information to create internal runtime structures. Types are not fully loaded until they are actually used, which improves startup performance. When a type is first accessed, the runtime reads its metadata, verifies it, and prepares it for execution. This process ensures type safety and correctness before code runs. Metadata and assemblies also enable lazy loading. The CLR loads only the required assemblies and types, rather than loading everything up front. This improves performance and reduces memory usage. Another important aspect of metadata is its role in exception handling. Exception types and their hierarchies are defined in metadata. This allows exceptions thrown in one assembly to be caught in another, even if written in different languages. Metadata also supports generics. Generic type definitions and constraints are stored in metadata, allowing the runtime to enforce type safety and optimize execution. Assemblies also define visibility boundaries. Types can be public or internal. Internal types are accessible only within the same assembly. This allows developers to hide implementation details and expose only required APIs. This concept of encapsulation is enforced by the runtime using metadata information. The CLR checks accessibility rules during execution to prevent illegal access. Assemblies simplify deployment. Because assemblies are self-describing, applications can often be deployed by simply copying files. There is no need for complex registration processes. This approach is known as copy deployment and is one of the major improvements introduced by .NET. Metadata also supports debugging and profiling. Debuggers rely on metadata to map IL instructions back to source code. Profiling tools use metadata to track method execution and performance. From a language interoperability perspective, metadata ensures that type information is consistent across languages. When a C# library is used in VB.NET, metadata ensures that the VB compiler understands the structure of the C# types correctly. Metadata also supports runtime services, such as serialization. Serialization frameworks read metadata to determine which fields should be serialized and how objects should be reconstructed. Assemblies and metadata are essential for dynamic loading. Applications can load assemblies at runtime using reflection APIs. The runtime reads the manifest and metadata to integrate the new assembly into the execution environment safely. In modern .NET applications, assemblies are also the unit of distribution through package managers. NuGet packages contain assemblies along with metadata that describes dependencies. The CLR uses assembly metadata to resolve these dependencies during execution. The relationship between metadata, assemblies, and the manifest can be summarized clearly. Metadata describes what the code contains. The assembly groups code and metadata into a deployable unit. The manifest defines the identity and dependencies of that assembly. Together, they allow the CLR to load, verify, and execute code reliably. From a developer's perspective, these components work silently behind the scenes. However, they are the foundation of many advanced .NET features such as reflection, dependency injection, versioning, security, and cross-language interoperability.
In conclusion, metadata, assembly, and the manifest form the structural backbone of the .NET Runtime.
Metadata provides rich type information, assemblies define deployment and execution boundaries, and the manifest defines identity and dependencies. Together, they enable safe execution, flexible deployment, and powerful runtime services. Understanding these concepts gives developers deep insight into how .NET applications are built, loaded, and executed internally, and completes the picture of CLR architecture.